So organics for this year, carbon has 4 available bonds. That's what you need to know, and you need to understand that. And obviously hydrogen will have 1 available bond, so it would easily attach itself to the carbon bonds there. So that's just showing it to you guys in terms of a Cooper structure. If you wanted to draw the Lewis structure, it would be like this. And then the hydrogen would have 1 available electron that is available for bonding. And then there we go as well. Okay, so that there is essentially showing us why carbon has 4 bonds, why carbon has those 4 bonds there. By Cooper and then by Lewis. Now for grade 12, you would typically just need to draw it in this form here, this first form. So let's first get into the important part of understanding how you name a particular organic compound. So you're going to first understand and learn these things. First, math is going to be for 1 carbon, eth is going to be for 2, prop is going to be for 3, Bute is going to be for 4, pent is for 5, and then we're going to do hex, which is for 6, hept is for 7, oct, and then that's essentially where I'll stop for now, right? And then we'll do the remaining 2, because I don't think it's that important, especially not for now. We'll do the remaining 2 in our classes, right? Okay, so those are just telling us basically our prefixes for our carbons. So for example, if we're dealing with something that had, let's say methane, this here would be methane. Ethane would be this, 1, 2. Now, eth basically tells us that there is, let me use a different color. Let's do that. Eth basically tells us that there's going to be 2 carbons, 1, 2. So 2 carbons attached to each other, and then 1, 2, 3, 1, 2, 3. But essentially, it's 4 in total. So if we have a look here, 1, 2, 3, 4. 1, 2, 3, 4. So there's 4 bonds still. So that's what you need to keep in mind, that carbon needs to have 4 bonds. And once you know that, you should be fine. All right, so now what we're going to do is we're just going to attach our hydrogens just for the fundamental and easy parts of this. So that is telling us that we have 2 carbons and then we have all single bonds between our carbons. So you'll see here that there is a single bond between the carbons. If there's a single bond between the carbons, what we can then say is, if it's single bond, it's going to end in ANE. So for example, this name of this compound is going to be regarded as ethane. There we go, ethane. Pretty simple and easy. Now let's take this a step further. Let's say we had 4. So 4 carbons attached to each other. It would be 1, 2, 3, 4. You need to make sure that you have 4 available bonds on each carbon. And then there's the hydrogens, there's the hydrogens, there's the hydrogens, and so onwards. There we go. Done. Now again, important to see that we have 4 carbons directly attached to each other, which would then entail that we should be dealing with a 4 carbon main chain, so bute. And then all we do from here is we say this. There is definitely single bonds only between these carbons. We'll get to the double bonds later on in our actual first class, but for now, just the single bonds. So single bonds here, what we're going to say is the following. So if it's a single bond, what do we know? It must end in ANE, yeah? Like we said previously. So what we're dealing with here is actually butane. Done. Simple and easy. So I would suggest you just draw out all of them and you figure it out. I shouldn't say it's figured out, but if you draw out all of them, all of the different size of our carbons, not size of carbon, size of our organic compounds. So if you go propane, pentane for 5, hexane for 6, heptane for 7, octane for 8, you draw it out, it'll be easier to see. What I also want to just get into now quickly is how they can confuse you slightly with just the shape of it. But now remember, you need to always look at continuous chain length. So for example, let's take heptane, for example, right? Actually, you know what? Let's do pentane. Okay, so pentane, if I do this, carbon, 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 carbon. What you want to notice here is that it's one continuous flowing chain, right? There's no going back or anything of nonsense. So there's no, essentially what I'm saying, there's nothing like this here. There's no this, 1, 2, 3, 4, and then for example here. So here, this is not a continuous chain, right? Because you essentially had to go back or you had to go up and come back. So it's not a continuous chain. Because it's not a continuous chain, this one here, for now, we are not going to worry about it. For now, we're not going to worry about this one here because it's not a continuous chain. For the first part, we're going to deal with these continuous chains. We'll deal with the non-continuous chains, like I said, in the actual class. Right, so anyway, let's go and attach our 4 bonds to each of these carbons. So here, this is also pentane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, whether I draw pentane like that there, in this weird shape that I've done, or if I draw it like this here, 1, 2, 3, 4, 5. And if I just fill in the hydrogens from here, you'll see that even though it looks slightly odd, all that has happened is that it was bent slightly. The actual organic compound was bent into this particular shape. So they took this one and they just kind of bent it into this here, but it's still the exact same thing. So what you want to see is the following. If you want to count the number of hydrogens and carbons, so here we obviously have 5 carbons. And the number of hydrogens you'll see is 12. And if you do the same, if you count the number of carbons here, you'll see that it's going to be 5 carbons and 12 hydrogens. So it's essentially the same thing because what I said earlier was it's one continuous chain. It's one continuous chain. Therefore, they're essentially the exact same thing. Right, so getting into grips with the continuous chain as well as getting into grips with knowing 1, 2, 3, 4, 5, 6, 7, 8. You don't really need to know more than that. If you do, 9 is non and 10 is dec. Obviously, that's just obvious. Non is 9, dec is 10, and that's essentially it from there. Please make sure you understand this stuff before we get to that first lesson, right? Just to understand, most importantly, how the number of carbons relate to the actual prefix of the name. So the meth, eth, prop, but, pent, hex, hept, oct, and then understanding the one continuous chain thing is very important, like we've explained here, the one continuous chain thing. Okay, so let's start with momentum for physics for this grade 12 year. So what exactly is momentum? So momentum is denoted by the symbol P, and basically momentum is a combination of mass and velocity. So it's the product of mass and velocity. Obviously, momentum is P, and it's going to be measured in kilograms because mass is kilograms, and then velocity is meters per second. So there we go. Momentum is measured in kilogram meters per second. Obviously, you know that mass is kilograms, velocity is meters per second. So how do we use this now? Please understand that anything that has a mass and has a velocity has a momentum. That's it. Now, let's go and do a simple calculation. Let's say they tell us that we have a toy car. Let's say we have a toy car with mass 0, actually no, let's actually make it mass 250 grams and moving at 10 meters per second. All right. Now, how do we go and calculate the momentum of the toy car? Calculate, handwriting. Calculate momentum of toy car. Right, so momentum is P. Momentum is equal to mass times velocity. Your mass is 250 grams. Now, how do we convert 250 grams to kilograms? Simple stuff. 250 times 10 to the minus 3, or 250 divided by 1,000. So this is basically 0.25 kilograms with a velocity of 10, and we have this as 2.5 kilogram meters per second. Done. There we go. Momentum. Also, momentum needs to have a direction. It's a vector quantity momentum. So typically you'd need to say in a particular direction. That's the important thing about momentum, right? Is you have to understand momentum is like a velocity, like you've learned in grade 10, and it's like force that you would have learned in grade 11. Momentum is based off direction, most importantly, which we're going to get into next. Right? So just to get into the basics, please note that when we have momentum being conserved, right? So when we talk about conservation of momentum, which is the next step. So conservation of momentum. What is conservation of momentum? Conservation of momentum states the following: that in an isolated or closed system, the total linear momentum remains constant. So in an isolated or closed system, the total linear momentum remains constant. Now, the wording is important there. When we say linear momentum, what are we talking about? So linear momentum means in the same direction. So if we're traveling in the x-axis, the momentum in the x-axis is conserved. If we are traveling in the y-axis, our momentum in the y-axis is conserved. If we are traveling, for example, on an inclined plane, then the momentum on that inclined plane would be conserved. That's the importance here. We have to understand that it's for that particular axis. So that's why it's linear momentum. Now, typically, the way I like to explain this is by three typical collisions, right? So when we talk about conservation of momentum, we talk about collisions typically. So when we talk about collisions, we have three fundamental types of collisions. So our first type of collision that we deal with is going to be a separate and separate collision, right? Now, when we're talking about separate and separate as a collision, we're talking about, for example, we have a car with a, that is just, obviously my drawing really is quite bad. So we're going to say this is car A, and we're going to say that this is car B, slightly bigger. And we'll say that this is 1,000 kilograms, and we'll say that this is, 1,500 kilograms. And what we have is currently this one at, let's say, a velocity of 15 meters per second, going this way here. And then we have this one at a velocity of 25 meters per second, going that way there. Now, this is before the collision. Now, what happens after this is, after they collide, obviously A is definitely going to go straight into B that way. What's going to happen after is, I'm going to say, okay, afterwards, what happens is that A ends up going with a velocity, actually, let me do this. A ends up having a velocity of an unknown here, right? An unknown velocity there. But what happens to B is that B actually ends up going off faster. And I'm going to say B ends up going off at, let's say, 25 meters per second, right? Going in that direction. So understanding that it's conservation of momentum, there's a formula we need for this. We need that the sum, that the sum of momentum before, which is initial, is equal to the sum, of the momentum final. Now, obviously, I really suck at writing sum or sigma itself. So what I normally do is I just do this here. I know that that's the sum, and that's just easier for me, and you're allowed to do that. That capital E, that weird capital E, is going to end up being our sigma or our sum. So we're saying that the sum of the momentum before is equal to the sum of the momentum after, but all with regards to the same axis, the same x-axis, or the same direction. Right, so now let's go and do this here. Momentum initial, we're going to deal with this as momentum A times velocity A initial plus, I shouldn't say momentum A, mass A is what I should have said there, mass A and not momentum A, but it is technically for momentum A initial, but mass A times velocity. Then we're going to deal with the momentum for B initial, which is going to be mass B times initial velocity, and then this should be equal to mass A final velocity plus mass B final velocity. So mass A, we know, is going to be 1,000 kilograms. Our initial velocity is 25. Mass B is 1,500 with an initial velocity of 15. But what we need to notice is in each of these cases, we're basically going to the right. So what I'm going to do is I'm going to say to the right is positive. Now, if you choose to the right is positive, it means you've got to choose that same direction as positive throughout for the entire equation. So not just for this initial year, not just for the one side, for the entire thing, we're going to choose going to the right as positive. So right is positive here and right is positive there. So there we go. Mass of A, we have the mass of A, we just don't have its velocity. So the mass of A we know is 1,000 kilograms. This was 1,500. So this is 1,000 into a final velocity, which we don't know. Mass of B is 1,500 times a velocity of 25. All right, so now let's just go and sort out what this final velocity of A is going to end up being. So we're going to have the first part, 1,000 times the 25, plus the 1,500 times the 15, and we're going to end up with 47,500 on this side. That's going to be 1,000 VF, and then 1,500 times the 25 is 37,500, and then we take, wait, I don't know why I put that as equal to. We take that over, it's going to be 47,500 divided by 37,500. So not divided, what am I saying? Minus 37,500 is 10,000. Oh, obviously it's 10,000. 10,000 is equal to 1,000 VF. So remember, when we took this positive over onto that side, it became a minus, and we have that as 10,000 there. And now we're just going to say 10,000 multiplication here becomes division there. So 10,000 divided by 1,000 is just going to end up with a velocity of 10 meters per second. And that's perfect. So now what that positive answer is telling us is that we are actually going to end up going to the right here. The positive answer is telling us that we are actually going to the right. So that is the concept of separate and separate. Now there's two other concepts that we're going to be dealing with in our classes. The other two fundamental concepts is basically the two other types of collisions typically that we deal with. So we did separate and separate as our first. The next one that we'll be dealing with is separate and together. And then the third one is going to be together and separate after that. So that's essentially the three typical types of collisions that you'll deal with. And do not forget that momentum deals with direction as positive. You need to have a direction as positive in your calculations. That's the most important thing to not forget. So yeah, that sorts us out with understanding momentum a little better. Hopefully when we start our classes, all of this will make a little more sense, because we're going to do a ton more of examples, questions, and introduce you guys into a little bit more intricate things in terms of momentum. See you guys then, yeah?